Okay, welcome back to Calculus 2. So in this video, we are going to talk about 5.3, the divergence and integral test. So far in chapter 5, we talk about the concept of sequence and series and whether they are convergence or divergence, sequence or series by looking at their pattern. And what we're going to do in 5.3, I'm going to show you two different tools to check whether your given sequence or series are divergence or convergence. So basically, I'm going to give you guys two different tests, and you're going to use this test, and you can easily see whether the given information is a divergence or convergence. So one tool is the divergence test, and second tool is the integral test. So let's take a look at those two. That's the main idea in chapter 5.3. So let me show you the concept of divergence test first, okay? So let's look at the definition of the divergence test. So I'm gonna highlight it with the blue color. So this is the definition. If you have a general form of the sequence AN and take the limit and then check it out whether they're heading to a certain number C, and then that is not zero, okay? Or the limit of the sequence form does not exist, automatically that series, I'm not talking about the sequence, if those two are true, then the series of that form will be divergence all the time. So let me write down this theorem. I know like it looks a little bit, abstract language. So here's a two condition. One is limit, you're gonna check where actually this sequence is heading toward. Check it out whether it is equal to 0 or not. Second, check whether this sequence with the limit does not exist. Either way. Or if you have one of the case, then automatically the series summation AN is always divergence. Okay, so this is the rule of divergence test. If you are satisfied with one of the conditions, and then the series, this is a series, will be always the divergence series. Okay. And somehow it is obvious, limit does not exist, and then the limit is not equal to 0, and then series is going to be divergence. Of course, they keep enlarging. So it might be so obvious theorem, but let's check it out. Okay. So exactly, I'm going to show you a couple example. We're going to apply the divergence test with the following information. So this is the series because there's a summation notation. And I know this is the AN spot. So we're going to check two different conditions. We're going to check the limit. I want to know where this AN is heading to as the N is getting larger and larger. So that is going to be your AN is N over N plus 1. So I want to know where they're going to. So many people forgot, I'm going to write a pink color. So when you determine the limit, the numerator, denominator equal degree, then you're going to reading the leading coefficient, correct? So the numerator degree is higher than denominator degree. The limit does not exist, right? This is from calculus 1. Numerator degree is smaller than denominator. The limit is always 0. So for example, 2x second over 2x second. Let's say you're taking the limit of this form, it's going to be 1 because 2 over 2 is 1. You have the same degree too, top and bottom. The second case, the numerator degree is higher than bottom, then limit does not exist. Last case, let's say 2x over 2x to the 5th, bottom is higher. The limit is always 0. So this is from calculus 1, how to calculate the limit when you have a fraction form. So therefore, we can apply this calculus concept in here because this is simply we're checking the limit. So we have n, top and bottom, we have the same degree. So there's invisible 1 and 1. So what is the limit of n over n plus 1? Just to 1. So we prove that this limit is not equal to 0. So if you are adding the next number, they're going to be larger and larger and larger because you're going to keep adding 1, 1, 1, 1, 1. So obviously the series is going to be divergence, but we are checking exactly this condition where this is a divergence series or not. And also you can check, right? You know, this one limit does not exist, but we already found out this is not equal to 0. Therefore, then the series, right, n over n plus 1, divergent series. That's our conclusion because of the condition of the divergent test. Does it make sense? So that's how you are utilizing this divergent test. Does it make sense? So you don't need to like, oh my God, like how do I know this is divergent or convergent series? So one method you could try is a divergence test. Just check their condition of the limit. Okay, so likewise, let's take a look at the second one. So same thing. This is the question whether this is series is a convergent or a divergent. So I'm gonna use a divergent test. If we fail the divergent test, it's going to be convergent, but let's take a look at it. I'm going to keep checking the first condition, limit as n approach to infinity where n over 3 and heading 2. Again, this is the first case. We have the same degree top and bottom, 1 over 3. So this is not equal to 0. So they are smaller, large, getting larger and larger. 1 over 3 plus next one, 1 over 3 plus 1 over 3. So unless it's not equal to 0, right? Unless it is a 0, that's going to be fixed convergent, but it's getting larger. So then we check the condition. Then this series we have divergent series. So obvious. Are you guys okay with that? So 5.3. They're showing you two different, tests, two different tools to check, easily it is a divergent test or not. Can you guys show me your thumbs up? Visually, maybe you can pause this video. Maybe it makes sense to you. Take a breath. So we are literally using the divergence test condition. Okay. So if you got this one, let's take a look at one more. Ooh, e to the 1 over n to the second power. So I'm just keep going, checking the limit. And then this is the an e to the 1 over n to the second. So what happened? We are checking the limit. How do I calculate the limit of the exponential function? The first method, if you remember, direct substitution, plugging in infinity into the n. So e to the 1 over infinity. Infinity, what is that? 1 over infinity, same thing. We know from calculus 1, it is always a 0. The bottom is getting larger and larger. Entire fraction is getting smaller, smaller. So this is going to be e to the 0 because 1 over infinity is a 0. So we prove that e to the 0 is 1. Again, this is not 0. So obviously they're getting larger and larger. So the series then, the series of that function is also divergent series. They're getting larger and larger infinitely. So that's how you're checking the divergent test. So make sure this is important condition either way. If there is a limit does not equal to 0 or the limit does not exist, the series of that form is always divergent. So these are the couple examples. Okay. I'm going to hold up here. Are you happy with that? So this is a warming up question. I'm going to show you a couple challenging questions when you're ready. I'm going to give you guys time a little bit and take a look at it. How you feel so far? Does it make sense to you? So can I go to the next slide? Okay, so I'm gonna keep reminding you of this divergence test. Check it out, the limit, okay? All right, let's go to the two more example. I'm gonna go down slowly. Ooh, this looks a little bit double function. So doesn't matter, we know what the divergent test. So this is AN. So we are going to check if this AN, when you take the limit, -1 to the n, n over y, I have a dot there, so get rid of it, n plus 1. So if this is not equal to 0, then it's going to be divergence. So let's check it out. So I'm going to write down a couple partial terms. So when you look at n equal to 1, -1, 1, 1 over 1 plus 1, so -1, 1 over 2. If n is a 2, -1 to the second, 2 over 2 plus 1, +1, right? Because it's an even power, 2 over 3. So this is -1 over 2. This is a 2 over 3, right? But wait. I'm actually taking the limit though, right? So what I'm saying is, actually, we need to think a little bit different approach. Hold up there. Let me get rid of it for a second. 1 second, because we are taking the limit. I'm not looking for the sequence. So this is we are taking the limit though. Are you following what I'm talking here? So we are taking the limit. So I don't need to really focus on the couple partial terms of the sequence. I want to know, so let's check it out. Just format. This one, if you take the limit, is always 1, isn't it? Because n over n, there's invisible 1 coefficient. And then -1, this is very tricky, but think about it. If n is odd number, -1 to the n is always -1. Am I correct? If n is an even number, -1 to the 1 is always a positive number. And then you're going to multiply with this outcome of when you take the limit, it's a 1. So either -1 or +1. Dun. 1 second. That's your limit. This is your limit. Limit value. We have a 2 different direction. Of course, none of the limit is not equal to 0. So we satisfy with the first condition, then the summation, they'll keep getting larger or constant anyway. This is going to be divergent. I forgot the -1. So this one will be a divergent series. Because we check the limit, you need to check only the limit, isn't it? So when you look at that, so let me just get rid of it. Here, 1. 1. So the limit is 2 cases. When n is odd, is always you're going to get the -1. If n is even, it's always going to +1, which is not 0. Therefore, the series of this function will be divergent series. Good. That's how you're checking. One more. Okay, this is ln. So I'm going to check if limit ln and approach to infinity, ln n to the second over 2n to the second plus 1. I want to know whether where they're heading to. Okay, so actually, I think I need to, sorry about that. There's no ln, so get rid of it for a second. So that's my typo. We're checking this one. So this one, again, what do you guys think? The top and bottom same, so 1 over 2. That's the limit of n to the second power, or 2n to the second power plus 1. So this is not 0. Of course, this series is a divergent series. So that's how you're applying the divergent test. It's always helpful to find out whether the series is a divergent or convergent in a shortcut. So this is a divergence test. Okay, so I'm going to show you just two tests. 5.3, honestly, it's a very, very short topic. So the second one, I'm going to introduce the integral test. So I'm going to hold up here. If you got that one, I love to see you guys invisible thumbs up. All right, everybody okay? All right, that's the divergence test. Let's take a look at the second two. I told you there are two. So the integral test. So integral test, here we go. A little bit of background. I'm going to use the same. So this is the second, oh, oopsie. Second test, integral test. So integral, we know that it helps us to find out the area, volume, force. There are so many ways you can utilize integral in many physics and mathematical field. So in this case, we have a function, and I want to know, like, let's say you have a series summation, and then let's say you have, very, very, interesting function. Let's say we don't know, but we are trying to know, or here you can say this is an. We want to know whether this is divergence or convergence. So especially when you have this an is a 1 over radical n. So this is the graph of 1 over radical n. Because this is very famous, one of the function, always is gonna be divergent. That's why I'm using it. So let's say your an is 1 over radical an, and this is the graph. And I want to know if you keep adding. What do you guys think about the summation? Obviously, it's going to be divergence, but I want to prove it in mathematical way. So let's think about step by step. So first step, I'm going to change this information. So we are actually doing infinity 1 over radical n. I want to know whether this is a divergence or convergence, right? Which it looks like this graph. And then if you just write down a couple series, it is going to be 1 over radical 1, 1 over radical 2, 1 over radical 3, 1 over radical n. They'll keep going and going forever like that. But wait. When you look at this summation, they'll keep adding. So you can use the integral, right? From 1 to infinity, because that's what exactly 1 to there keep going infinity. And I have an, 1 over radical n. And if you take the integral, okay, you can find out this relationship, because this one, they are stopping at n somewhere here. But let's say I'm going to continue up to infinity. So there's a relationship with the inequality because n is smaller than infinity. Does it make sense? Can you set up this logical statement? Let me one more time. My question is, I want to know whether this series is a divergence or sequence. And I wrote down a couple partial series of that form. So it's going to be Sn equal to I stop at n because they are going to Sn. But mathematically, they're keep adding all the area of this function. So this is exactly corresponding to the integral concept. But I'm going to make it a little bit large arrow up to infinity. So I can set up this inequality. If you're adding this summation, it should be less than integral from 1 to infinity with the same function. So the question is now, if you check whether this is divergence or convergence, if this one is divergence, this is going to be divergence. If this is a convergent, this is also convergent, isn't it? Squeeze theorem. So all you need to do, I'm going to just calculate the integral. Integral 1 to infinity, 1 over radical n, dn. So we're going to take the integral. That's going to be, oh, not the summation, integral. So this is a 1 over 2 n to the negative half exponent. Are you following? So that's 1 over radical n. And now I'm going to take the integral in negative 1 over 2 plus 1 divided by that exponent from 1 to infinity. So therefore, I can flip this one to n to the positive 1 over 2, 1 to infinity. So that means a 2. This is a 2 radical n from 1 to infinity. So we subtract infinity minus 2 times 1. So this is going to be infinity. This is going to be 2. Infinity, whatever the number, is infinity. So we prove that this information, my bad, this information, we prove that it is divergent. Therefore, the question that you're looking for is also divergent. That's how you're using the integral test. Because this is a too complicated function, 1 over radical n. Well, like, you could use maybe the limit, but I'm showing you the second way, the integral test. So based on the squeeze theorem, if this is the summation is going to be smaller than the entire summation from 1 to infinity, if this is a divergent, that is a divergent. If that is a convergent, that is a convergent. So therefore, simply you're going to calculate the integral and see the answer. Okay, so this is the one popular example of the integral test. I'm going to do one more, but I'm going to hold up here. Does it make sense to you? I hope you guys are happy with that. Sounds good. All right. Now I'm going to keep changing the function. So let me do another example. So this is a very important example. Example 2. Let me change the color. Determine, same thing. The infinity, the series. What if I have n to the third? Is it convergence or divergence? We're gonna using integral test. So that's the question mark. So we know this one, if I write down a couple partial term of this series, 1 over 1 to the third, 1 over 2 to the third, 1 over 3 and 3 to the third, and they say let's stop into the third. So this one, I want to know some relationship. Whatever this is summation, it's similar, but 1 to the infinity with the same function 1 to the third. That's going to be smaller, isn't it? So we can set up this relationship. If this is divergence, this is a divergence. If it is a convergence, this is going to be convergence because of the squeeze theorem, right? So let's check. All you need to do, we are going to calculate this integral. Dun, 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 dun. We talk about integral all the time in calculus too. So let's take a look at the integral. 1 to infinity, 1 over n to the third. And then dn, I have to write dn. So let's take a look at, that means 1 infinity, n to the negative 3 dn. So n to the negative 3 plus 1 divided by negative 2 from 1 to infinity. So that's going to be n to the negative 2 over negative 2, 1 to the infinity. Yes. So that means negative 1 over 2. You can flip this one, 1 over positive n to the second. So remember, you talked about it, x to the negative 1, 1 over x. X to the negative 2, 1 over x to the second. That's why n to the negative 2 is a 1 over n to the second from 1 to infinity. Almost. So now I'm going to subtract negative 1 over 2. 1 over infinity minus 1 over 2 times 1 over 1. So what happened? This is going to be definitely, what do you guys think? Oh, we are not taking the limit, my bad. But let's calculate this multiplication. So negative 1 over 2 times infinity is still infinity. But anyway, this is going to be 0, right? And then I'm gonna change this one, double negative, positive, and 1/2. So what happened? This is going to be 0. I told you 1/infinity, it's a 0. And then this is going to be 1/2. So this is a convergence. They're heading to convergence. So therefore, the question we are going, it is going to be convergent. This series is going to be also convergent series. That's the answer, because we are using the integral test. According to the squeeze theorem, we prove that the right side is a convergent. Therefore, the left side should be convergent as well. So how you feel? Both the divergent and integral test, divergent test, integral test, it's pretty helpful, right? It's pretty helpful. And I'm just going to write a couple sentences here, but I'm going to hold up here. Does it make sense to you? Does it make sense to you? You can pause the video and think about it, maybe come back. So from this observation, I can make the conclusion of the integral test. So let me go down. So from here, integral test, we see that it's very useful. Make sure you can use this one for only the function that is continuous. Suppose f of x is a continuous, positive, and decreasing on the interval. So what I'm saying is 1/radical n, 1/n to the third. When you look at the graph, it's the graph. This is the graph. They are going to be positive outcome, continuous function, and decreasing. When you have this satisfaction, then integral test is gonna work. If you have a discontinuous, if your outcome is negative, or if you have an increasing function, integral test never gonna work. Okay, then integral test works. So for example, n to the third, this is a positive function. Integral test is not going to work. So you have a very special like function, decreasing function, positive outcome, continuous function, then you can use integral. So if you satisfy this one, then first, if you have a k through infinity, let's say I have this integral. Let's say it is a convergent according to the squeeze theorem, then we know is also convergent. In other words, if this integral is divergent, then the series that we are looking for is also divergent according to a squeeze theorem. That's the integral test information. You can get it. All right, we are on the good track. Okay, so if you got this one, let's take a look at it. Okay, so I'm going to hold up here. So I think this definition is much, much simpler. Okay, because we just proved that by looking at the examples. So the textbook looks a little bit, too much information, but let me show you the textbook information. So let me go down slowly, okay? Slowly. So this is the same thing. They say, assume that the function is a positive, continuous decreasing. And then according to the squeeze theorem, if this is the, sequence, convergence, this is a convergence. If this is divergent, this is divergent. So that's exactly those two slides is talking about. Sometimes the inequality is going to be changing, but you don't need to really worry about that. Just check what the integral outcome is, a convergence or divergence. And also it's only working for the decreasing function. So I just summarized this information up there. So I think this is just simple, definition of the integral test. And then we just prove that by looking at the couple examples. Okay. So I just want to do 2 more examples because I want you guys to practice more with me. So let's take a look at, this question. So what are you guys going to do? I want to know whether this is a convergent or divergent test, isn't it? So let's take a look at it. So what are you guys going to do this one? So in this question, we need to think about it. We are going to use integral test. So as I mentioned, what are you guys going to do? You're going to write a couple things. So this is, we have Sn 1 over 1 to the 4 plus 1, 2 over and 2 to the 4 plus 1. You keep going, n over n to the 4 plus 1. So they're stopping at n. I know that this is going to be from 1 to infinity, n over n to the 4 plus 1 dn. We are going to take the limit. If this is convergence, this is going to be convergent. If it is divergent, that is a divergence. So you can take the integral of that. But as you see that, Professor Ben, this is so ugly. How to take the integral n over n to the 4 plus 1? Right? It's not simply, whatever. So you could do actually separate it. N over n to the 4 dn plus, you can separate n over 1. Oh, I have a little mistake. So 1 second. So this is a question mark, right? Because this is not going to be separated. This is a 1 fraction, n over n to the 4 plus 1. So now you might be looking for another testing, integral test, like, this is a little bit difficult to take the integral. Same thing here. How am I going to take the integral? Something you're going to find out the partial, and then 1 over 2n minus 1. You need to take the integral. So this is a little bit bugging me, isn't it? This is a little bit bugging me because the integral test, it's a little bit challenging to take the integral. So that's why I'm gonna come back to this question. The last test I'm gonna introduce, P-series test. This is a very, very, very super powerful test, P-series testing, okay? So I'm gonna show you the definition of the P-series and I'm gonna come back to the other question. So what happened is, look at that. If you have a function with the fraction, and then it is a 1 over n to the p. For example, you might have 1 over n to the 1, or you might have 1 over n to the second, or you might have 1 over n to the 4. Let's say you have a keep different, p number as an exponent right there. This is the rule. If a p is 1, simple, the series is always divergence. If a p is a 2, the series is going to be always a convergent. I know this is surprising, but this is the rule. If you have n is a 1 is always divergent. If n is a 2 is always convergent. So therefore, here is a more specific rule. If the p, whatever the exponent is less than 0, which is a negative number, or that is exactly 1, always the series is going to be divergence. And then whatever the p is greater than 1, like a 2, 3, 4, 5, 6, 7, it's always convergent. So I will show you a couple examples. Just hold up there. You don't need to worry about it. I'm going to come back. So what I'm saying is, let's say we have infinity 1 over n, right? And then let's say I have an infinity n equal to 1 over n to the second. Let's say I have n equal to 1 over n to the third. Let's check. whether this is divergence, convergence, divergence, convergence, divergence, convergence. So instead of using p-series, I'm going to use integral test. So it means that we can take the integral directly, right? So integral test, whatever this is, summation is going to be less than integral 1 to infinity, 1 over n, isn't it? So if you take the integral n to the negative 1 dn, and then if you take the actually integral of the 1 over n, they're going to be ln. So it is going to be ln n from 1 to infinity. So this is ln infinity minus ln 1, which is, this is infinity minus 0, infinity. That's why when p equal to 1, we got this series is a divergence. Am I correct? Very, very, very true. I'm going to go to the next one. Same thing. I'm going to take the integral because this is a smaller than 1 over n to the second infinity. So let's take the infinity. This is n to the negative 2 dn, 1 to infinity, and negative 2 plus 1 over negative 1, 1 to infinity. I'm literally taking the integral. So this is negative n to the negative 1, 1 to infinity. So let me change it. This means negative 1 over n from 1 to infinity. Because the n to the negative 1 is 1 over n. Plugging in negative 1 over infinity minus 1 over 1. Again, this is a 0. Plus 1, 1. Ooh, this is a convergent. So when p equal to 2, we just proved that it's a convergent. Exactly, this is a p series rule. Last one, let me take a look at this. Last one, I'm going to take the integral test, 1 over n to the third, dn. Yeah? So what happened? This is n to the negative 3 dn, 1 to infinity. Take the integral, and negative 3 plus 1 over negative 2, 1 to infinity. So this means negative 1 over 2, n to the negative 2. So that negative 1 over 2, 1 over n to the second, 1 to infinity. So you're going to subtract large, 1 over infinity, minus negative 1 over 1, 1 over 1. So this is going to be anyway 0, because that 1 over infinity. So 0 double negative plus 1 over 2. I got you. This is also convergent. So when p equal to 3, yes, we got convergent. When p equal to 2, it is convergent. When p equal to 1 is only divergent. So that's why this rule is true. I told you if a p is less than 0 or equal to 1, always a divergent. Okay? And the p is greater than 1, it is going to be convergent. So you don't need to calculate it at some point. Okay? So therefore, we can think about more complicated function. We can take more complicated functions. So let me just go back here. Am I really take the integral rule? No. Just check p series rule. So p is less than 0 or p equal to 1, always a divergence. P is greater than 2, equal to 2, always a convergence. So p, or you don't need to calculate anything. This series is going to be convergent. What is a p? Is a 2 over 3. What is a 2 over 3? Less than 1, correct? So what do you guys think? It is going to be divergent. This one, when you have p is going to be half exponent because that's a radical. Less than 1, this is divergent. This one is what? N to the 1, n to the 1 over 2. That's your p. So n, 1 plus 1 over 2, n to the 3 over 2. Okay, p 3 over 2 is greater than 1, so it's going to be convergent. Okay, so you can simply do check whether the given series is a convergent divergence by using either divergence test, integral test, or p-series rule. So only p-series rule, just remember, when you have this format, 1/, simple fraction. Okay? So for this two question, I will show you another testing in the next session, and then I'm coming back. But again, you could check with the limit divergent test, right? So check the condition limit, right? N over n to the 4 plus 1. We know that bottom is a larger, so this is a 0. So this is a 0, that means what? So if you go back, up, divergence test, if it is not equal to 0, then divergence, but it is a 0. So what happened? This one is going to be convergent. They're heading to 0. So you can check the limit as well. So you can, sometimes integral test is not going to work. You need to think about other tests, either divergent test, integral test, or p-series test. Depending on the function, you have a different testing to see whether the series is a convergence or divergence. So that's why I show you 3 different testing today: divergent test, integral test, and p-series test. So these are 5.3, and you can finish everything. So next session, 5.4, I'm going to show you comparison test. That's also very short topic, but there's a couple property we need to talk about it. So I will focus on only 5.4 in the next session. Only today, we're going to focus on 5.3. And check it out. Go back to the textbook. Look at the definition one more time. What the divergence test, what the integral test, what the p-series test. They have a different, condition to see whether the series is a divergent or convergent. Okay, so that's all about today, 5.3. I hope everything is clear. If you have any question, email me, or I do have an office hour. You can make appointment. So feel free to, email me, and now you can finish your 5.3 quizzes. Okay, so I will stop recording at this moment. Thank you for everyone. See you in the next video. Bye-bye.